All right, everybody. It's time to get started on part 2 of this lecture series, or maybe part 3, depending on how you count. The sun's out. The cold weather is temporarily gone, so hopefully this will be a warm and sunny introduction to how to calculate power in the real world. And so why are we doing this? So the weird thing about power is that you only do a power analysis before you run your experiment. So like with our null hypothesis significance testing paradigm, we run the experiment, we get the mean of our sample, we get the standard deviation of our sample, and then we try to determine whether the mean is significantly different from what we thought before we ran the experiment, or maybe we're trying to test whether two means are different from each other. We do the analysis after we run the experiment in either way, right? For power, though, you run that analysis before you do the experiment, which is odd. Because it depends on a number of different things, some of which come from your experiment itself. So power is dependent on your sample size, or n. It's dependent on your alpha level, and I mentioned before that we can change both of these things at will. The two things that we can't change entirely at will are number 3 and 4, which is the mean of our sample, and then the standard deviation of the sample as well. Those depend on what data we get from the real world. The problem is, though, that if you already know all these things, and you know all these things once you're done running your experiment, then calculating power is not going to tell you anything new. So there's no point in sort of adding a fifth number to all four of these. It's just already there, basically. So what you have to do to calculate power, or the only sort of circumstance where it makes sense to calculate power, is before you run the experiment. But then the problem there is that you don't know what the values of 3 and 4 are. And these two you can just set to be whatever you want them to be. So the tricky part is, though, that normally people want to analyze power to try to figure out what n should be, what their sample size should be for their experiment. That's the one of these they like to sort of leave out as they're doing this power analysis. Because remember, if you have all four, you know what the power is. And then if you have sort of 3 of these 4 and then know what power is, you can calculate what the remaining sort of parameter is ahead of running the experiment. So what people do is use power analysis ahead of time to answer questions like, how many subjects should I run in my experiment, which is a question I get from students all the time in this class. And I'm sorry that I'm giving you such a long, convoluted, and complicated answer, but this is how you answer the question. So the only way we can answer this question is by, again, sort of unfortunately, taking shots in the dark as to what the mean and standard deviation of the actual population distributions are going to be. So we have to guess what the values of 3 and 4 are going to be before we actually find out what the values of 3 and 4 are going to be. And by doing that, we can come up with a reasonable number for n before we run the experiment. Okay, so that's the weird part of this whole thing. We're making guesses about the parameters we want to find out about by running the experiment before we run the experiment. So it's like, what's the point of doing any of this? But remember, statistics is just an elaborate guessing game. And before we run the experiment, we make some guesses. And then after we run the experiment, we make some different guesses. But hopefully the guesses we're making after we run the experiment are more reasonably informed than they were before the experiment. So we learn a little bit each time we go through this process. It's not all a completely weird waste of time. All right, so let's make it happen. I'm going to show you an example of how we can actually crunch out some actual power numbers for, in this case, an example set of data. And then in the final lecture in this series, I'm going to show you how to do it for a real set of data, a couple real sets of pilot data that I collected from students, or students collect under my supervision collected a long time ago. But let's not get ahead of ourselves. Let's start out by making it really basic. We're going to go back to sort of this VOT paradigm and say we're going to hypothesize that the mean VOT of some batch of unaspirated stops is 0. And then ahead of time, we're going to decide we're going to collect 9 different measures from our sample of VOT, or of unaspirated stops. So our sample size is going to be 9. And we're also going to guess that the standard deviation of the sample will be 30. Okay, so again, this is not like trying to answer the question of how big should my sample size be. In this case, I'm just trying to show you how to calculate power in this example when you know all 4 of those values. So we know these 3 things here, and then we're just going to keep alpha set to 0.05 like it's conventionally set to. And so we know all 4 of those parameters. We just can use them now to calculate power for the results of this experiment. So we're going to figure out first what mean value of VOT do we need to get from our sample to reject this null hypothesis. So these are our hypothesized values. At what point on the VOT line would we say, where would we get a mean value of VOT to say, no, I don't think the mean VOT of these guys is actually 0. I think it's something different. And again, this is a question I normally ask in class, and then I just expect people to know it. When I was like going through these notes last night, putting them together, I realized that the answer is kind of complicated. So I don't know why I've been expecting people to just be able to answer it on the fly. So I'll walk you through how to calculate that answer. But basically, the short answer is we'll reject the null hypothesis if the sample mean is 19.6 or greater. And I'm just going to focus on that greater than option in walking you through the math of this. But actually, on the other side, we'd reject the null hypothesis too. So if our sample mean was less than negative 19.6, then we'd also reject the null hypothesis, just because we'd be so far away from 0 that it would be reasonable to say, I don't think we're getting this result by chance. Okay, so how do we get that answer? We'll just assume we're running a 2-sided z-test here, even though that's not a real thing, but that makes the math a little easier for us to digest. And so remember that 95% of the hypothesized distribution is going to be within 1.96 z-scores from the hypothesized mean, which is 0. So this is that old 68%, 95%, 99.7% rule for normal distributions, except we're tweaking it a little bit. It's not 2 standard deviations are within 95%. It's 1.96, technically speaking, but it's almost 2. So most of our distribution, 95% of it is going to be within those 1.96 z-scores from this hypothesized mean, which is 0. And on either side of that, we're going to get 5%, the remaining 5% of the distribution. But what we want to do, basically, knowing all this, is that we have a z-score, which is basically our criterion line in this setup. And then we know what our hypothesized mean is. We know how many items we have in our sample, and we know what our hypothesized standard deviation is. On the basis of all those things, we can figure out what the mean should be to kind of get us past, the sample mean should be to get us past that criterion line. And again, normally I'd write all this math on the board. I think maybe I'm making things a little more efficient by just plopping it out all here at once for you. So you don't have to, number one, read my handwriting, but also don't have to sort of process all these little like typographical details as well. But basically, like I said, what we got here is we're calculating a z-score. This is our equation for a z-score. It's a little different from the way you might remember it, though, because on the bottom, instead of just standard deviations by itself, it's got our estimated standard error, because we're looking at a sampling distribution here. So we've got a standard deviation of our sample divided by the square root of n. And again, we're just like positing these values here so we can just put them in to figure out what power is at the end of the day. And then we're trying to figure out what this x bar is, what sample mean we need to sort of say we have a significant effect. Mu, we're just saying is 0. And then z is just this criterion line. We're saying anytime we get 1.96 or greater, we're going to say, we have a significant result for our experiment because the p-value is going to be 0.05 or less. So you just plop these numbers in here that I told you before, 30 for the standard deviation, 9 for n, the number of items in the sample. Do some simplification here. The square root of 9 is 3. 30 divided by 3 is 10. Bring that over to the other side, and we get x bar equals 10 times 1.96, or 19.6. So with this number of items in our sample and with this standard deviation, anytime we get a sample mean of 19.6 or greater, we say, oh, I think the actual mean of this population is significantly different from 0. It's probably greater than 0. And if you are an eagle-eyed observer, you might note that if we're running a 2-sided test, the same thing is going to be true on the other side of the distribution. That is going to have kind of a negligible effect on the power calculation, but just to be honest, it's over there. So that would be, in the grand scheme of things, you'd have to account for that as well. But we're just focused on this greater than option for now, just to keep it relatively simple for all of us, because it's complicated enough at this point. Okay, so let's say we have this criterion now, which is basically any sample mean greater than 19.6. We're going to say there's a significant effect. It's significantly different from 0. And let's say we actually have a mean VOT for unaspirated stops of 30. And the standard deviation here is going to remain the same, but this mean value is going to be different. So before, in our little setup with the graphical depiction of this whole thing, we had means of 0 and 3, standard deviation of 1. Now I'm changing it a bit. We have means of 0 and the actual mean of 30, and the standard deviation is 30. Okay, what does this mean? For our power calculations. What we have to, the question we have to answer is, what is the probability, given our testing criteria, that we will miss recognizing that the actual mean of the VOT distribution is not 0? So to say that again, remember we have this null hypothesis that the mean of VOT here is 0. So we're going to default to that unless we have good reason not to think that that's the case. So what's the chances, or what are the chances, what is the probability that we will miss recognizing that we're wrong about that? With our God's eye view, we find out here that the actual mean value is 30. We might still miss that, though. It's possible that we will not recognize that the mean is different from 0. How do we calculate that probability? So first of all, calculate how far in z-scores the criterion level is from the actual mean of the distribution. So we know how far that criterion is from the hypothesized mean. It's 1.96 z-scores away. But here we're going to take a different perspective on it. We're going to say, well, how far away is that from our actual mean, which is 30, and conveniently has the same standard deviation as what we had before. And again, this is just the arithmetic involved here. So we know that the x bar, the criterion line, is at 19.6. We know that our actual mean here, our actual mu, is 30, and these numbers on the bottom stay the same. We're just trying to figure out what the new z-score is here. And I guess if I had more time, I could have put like little subscripts on these guys to say like mu sub a for actual mean, and then like z sub a for actual z-score, or actual z-score if you want. So proud of my daughter. She's learning the alphabet. She's turning 3 on Thursday, and she says Z, like a true American. I don't know how well that's going to fly when she starts going to school, but we'll see. For now, we can calculate z-scores, not z-scores. And anyways, on the bottom of this equation, we're going to wind up with 10, again, like we had before. On the top, we're going to wind up with a value of negative 10.4. So we're on the left side of the actual distribution here, right? So our criterion line is at 19.6. That's on the left side of a distribution which has a mean of 30. So when you do all the math here, you get a z-score of negative 1.04. Okay, what does that mean? Again, we're trying to calculate a probability here that will miss recognizing that the actual mean of the VOT distribution is not 0. We know that our criterion line is at negative 1.04. So what proportion of our distribution is to the left of that? That'll give us that percentage, that likelihood measure that we're thinking about. So we can actually calculate this two ways using R, p-norm of negative 1.04, or we can put all this mess in there, which is to say our criterion line of 19.6, our mean, and then our standard error estimate of 10. And it winds up in the same place for both equations. We're at 0.14917 for whatever that's worth. That's about 15% of the time we're going to miss recognizing that we have an actual mean different from 0 in this setup. So our beta value is 0.149. That's the amount of the purple distribution to the left of the criterion. And then if we calculate the flip side of that, basically 100% minus 15% gives us about 85% of the distribution on the right-hand side of that criterion line. So our power, in this case, calculated from what we know about the world in this fake little example, our power, 1 minus beta, is 85.1%, or 0.851. Okay, so that's a very simple or simplified walkthrough of how you calculate power. And normally, since there really is no such thing as a z-test in stats, you wouldn't be calculating it exactly this way. You'd be calculating power for like a t-test or something like that. And also, you wouldn't be doing it by hand because R can just do it for you. But if you are curious, this is kind of the underlying structure of how the numbers play out. And we're not actually going to have to do it this way again. I'll show you how to do it the easy way in the final video here. But basically, to recap what we found out, 85% or 85.1% of the actual sampling distribution will be to the right of the 19.6 criterion in this experimental scenario. And as a reminder, there is a conventional level of power as well as a conventional level of false alarms. But this conventional level of power is 0.8. We want to have a power of 0.8 or greater when we run an experiment, because that's a reasonably good chance of finding that there's a significant effect or something significantly different from our null hypothesis. And in this case, we're better than that. We're at 0.851. So we're good to go with this experiment. In this case, we could do it with just 9 items in our sample. But you might not know what the answer to that question is in your own experiment. So how do you answer that question without knowing all these background details first? That's the next question we need to answer. However, I'm going to take a little break before I get into that and talk to you a little bit about something else, which kind of is a setup for answering that final question. So I'll remind you that we have different sorts of conventional levels for false alarms and misses. I've talked about that multiple times before, but our conventional hypothesis testing settings are biased against false alarms, so we're only supposed to get those 5% of the time at the expense of a few more misses, which we get 20% of the time. And this is not sort of the optimal criterion setting if you just want to minimize errors overall, right? Minimize, I don't know what the exact number is, but to minimize errors completely, both types of errors altogether, you would wind up with the exact same numbers of both. And again, like I said, I don't know what the exact same percentage for both of those would be. I don't know if it's 10% or something like that. But these both add up to 25%. You could get fewer mistakes than that, but the conventional settings are biased, like I said, against making these mistakes, against making the false alarms mistakes. It's because as human beings, we tend to make more false alarm mistakes anyways. So the conventions guard against that tendency. But in other intellectual circles, that's not necessarily the case. In other places in the world, they're willing to make more false alarm errors in order to reduce their number of misses. So one case where you might think about this is going to see your doctor. So doctors are less inclined to tell their patients that everything's okay when, in fact, something is truly wrong with them. So, for instance, if you had something truly wrong with your health and you go to your doctor and then 20% of the time the doctor just misses the fact that something's wrong, would you still go to them? Would you be getting more second opinions than you do normally? I don't know, but maybe you would probably start thinking that doctor is not super helpful or reliable. Like I said before, though, thankfully for us, nobody dies if a linguist is wrong. Nobody dies if a linguist misses something. It's just nice when we can kind of capture it, when we can notice that significant effect when it's there, because that gives us a better understanding of how the world works overall. And thankfully, nobody's life is on the line. But we might want to shift these conventional limits in different contexts, and we can if we want to. One thing I'll add to this, which I was alluding to before, is that another culturally different aspect of power analysis that we need to get used to is the fact that effect size matters. And so this is something above and beyond just the idea that you might get a significant effect. There's also a question of what is the magnitude of that significant effect. And that will give us sort of a clearer picture of what might be going on in our data. Okay, so what do I mean by effect size? Well, I'll give you another example here from the medical world before I get into that. And this is also maybe a bit of an example from the American world. But for instance, if you were testing a drug that cost $1,000 and found that it improved symptoms in only 2% of its patients, would that be worth the expense? So questions like these come up, I think, more in the public discourse in the U.S., where we don't have a public healthcare system like the one that exists in Canada, and not everybody's, privy to the privileges of being a part of that system, and you kind of have to pay one way or another to get into it, whether it's through having insurance through your work or just buying it on your own. And then also, when you have an insurance company, they are willing to pay for some things that might make you sick, and they're not willing to pay for other things that could help you out. Sorry, I said that totally the wrong way. So they insurance companies don't pay for everything. There are some things they might not be willing to pay for, depending on your plan. I don't think they would ever pay for something that would make you sick. They might pay for something that will help you get better if you are sick. And I'm thinking about this a little bit because, just to give you a personal example, my dad was diagnosed with a condition called multiple myeloma about 7 years ago. And he just turned 84. My daughter's about to turn 3. He turned 84, so there's a bit of an age gap there. But he's done well with it, in part because he's been able to get good care through his insurance company. Because I think when he was diagnosed, they said the survival rate, 5-year survival rate for him, for people of his age, would be like 50%. So he's beaten the odds a bit with that. And partly it's because they have developed new drugs to help treat the condition. And they came up with a new one a couple of years ago, and his insurance company was like, well, we're not going to pay for it. It's too expensive. And, it's not like a proven remedy at this point, that sort of thing. And he's like, well, when you are paying for your own healthcare, you're more likely to pay a lot, right? And it cost in the neighborhood of thousands of dollars. And they're like, man, this is going to bankrupt us or something, but we need to keep living, right? These decisions are decisions you need to make if you are an American sometimes. But thankfully for my dad, the insurance company eventually kicked in and footed the bill, which is great. And he's still around to talk about it. But when you are like making these decisions about like how much benefit do I get out of how much cost do I have to like lay out to get that benefit, you start thinking about what are the effect sizes of, say, using a drug. And lo and behold, it's actually getting so warm here that I'm going to lower the window and hopefully there won't be too much noise from the outside. Anyways, enough personal stuff. Statistical moral to keep in mind. If your N is large enough, you are almost always going to get a significant effect. So this is why we talk about the magnitude of these effects. Like I said before, like if you think about changing N in the testing paradigm, it's going to squeeze the standard deviations of those sampling distributions. So even if there's like a minor difference between your hypothesis and reality, like a VOT difference of 3 milliseconds, if you crank N up to some very large number, like 1,000 or 10,000 or something, you will at some point get to the point where those distributions are sort of skinny enough that it will enable you to get some significant effect. And you can say, oh, look, my p-value is less than 0.05. Publish my paper, please, because I showed that something out there matters in my experimental paradigm. But for that reason, people have more recently commonly thought of effect sizes. Like, why don't we report effect sizes when we do get significant effects, so we get a sense of like how much does this actually matter, not just in the medical world, but in the VOT world as well. Okay, so what do we mean by effect size? So effect size is basically that difference in the two means, the difference between the actual population mean and the hypothesized population mean. In the example we just worked through, that would be 30. In the example from the previous video, that was a difference of about 3. And again, in this case, you won't know necessarily what the actual population mean is. If you're just running a one sample t-test, you'll just get that sample mean, and you can see how it differs from your hypothesized mean. In a 2-sample t-test, you'll get a sense of what the difference between the 2 sample means are, and that'll give you an effect size that way. Sometimes you're going to see this referred to as treatment mean minus control mean, and this is again borrowing from the language of medical science, where there might be a control group who gets like the placebo replica of the drug, and then there's a treatment group that actually gets the drug, and how much does that change their life compared to the control mean, which apparently you normally think their lives wouldn't change at all just by taking a placebo, although sometimes it does. Anyways, this is the sort of raw effect size. And then on top of that, you can calculate what's called a standardized effect size, which is this difference, actual population mean minus hypothesized population mean. Take that effect size and divide it by the pooled standard deviation of your 2 samples or whatever your sample is in your experiment, and you get basically an effect size that's going to look like a z-score to a certain extent. And this standardized effect size is often referred to as Cohen's d, because the guy who came up with this whole idea of effect size and standardizing it was a guy named Jacob Cohen. He invented this measure and argued for it pretty eloquently back in the 80s, or in the 20th century at least, and now it's becoming more and more influential as we actually report statistics in social sciences. So I'm going to make one more video for this series, and we'll kind of use this as context. We'll calculate a few effect sizes, but basically what we want to do is answer the question, how many subjects should I run in my experiment? And again, this is something you have to do before you run the experiment, so I'll show you how to do that. But for now, I've said enough, and I'll see you again still in the sunny afternoon here, and hopefully in a few minutes.